Hey everyone, today we're going to talk about the Reynolds transport theorem. So we're going to seek to define a theorem that's going to relate the time derivative of an extensive fluid property to a control volume. So first we need to define the intensive and extensive fluid property. So extensive properties depend on mass and intensive properties do not, or maybe properties per unit mass. So what we want to do is relate this extensive property to this control volume in the solid circle, but since the fluid's moving, it's not going to stay in the control volume. So we're going to have to follow this fluid and follow the mass in this fluid so that we can figure out how it's relating to this control volume in the solid circle. So it's going to start out in the solid circle, and then after a short time it's going to move into the dashed circle. So we can divide these three regions up into three regions. If you imagine this is actually a 3D sphere, we have region 1, region 2, and region 3. So first we have our extensive property as a function of time, and this is representing if we were following the fluid around, then we have zeta at t plus delta t minus zeta of t is equal to, then now if we're going to relate this to our control volume, then we have the property at region 2 and 3 at t plus delta t. That's there. That's because that's where the fluid is at after this short time delta t, minus zeta 1 plus zeta 2 at time t, because that was where it started out. Then if we look at this region zeta 3, this third region, then we can see that actually it would have had to cross this boundary here between regions 2 and 3. It would have to cross this control surface to get outside of the control volume. So if we want to measure the amount of mass that's in this third region, or any property that relates to mass, then we can take the surface integral as it leaves the control volume through this control surface over there, and that would give us the volumetric flux of the mass, or the mass flux. And then we have to multiply it by our time step delta t, and that will give us the total amount that it's crossed over there in however much time we're measuring. And we can do the same thing for region 1. That would have also, any mass that was in there would have come and it would have fluxed through this surface, and it would have been some other kind of fluid particle because it's not in our dashed circle. So we have these surface integrals instead of region 3 and region 1, because anything that was over there, it must have passed through the control surface. And then if we just divide by delta t, and we combine the inwards and outwards surface integrals, because it's all, we just integrate over the whole surface, and the sign will determine whether it's leaving or entering. Then we end up with this expression. So next we want to take the limit as delta t approaches 0, and that is going to give us the definition for the derivative. So the left-hand side was the fluid particle as it is traveling through the fluid, and it's going to be the total derivative because it does not depend on space. It's just we're just following the fluid around, and the right hand side is going to be a partial derivative of this capital zeta with respect to time, because this zeta on the right hand side, it relates to our control volume, and it's going to depend on both time and space. And then we also have the surface flux through our control surface. So next, if we rewrite this capital zeta on the right hand side as the integral definition relating to the control volume, then we get the traditional expression for the Reynolds transport theorem. So this is going to relate the time derivative of some extensive fluid property to a control volume. And we're going to use this to derive the energy equation and momentum equations. It's fairly intuitive if you think about it, because basically what it's saying is the time rate of change of this property is equal to the amount of the property that's coming through the surface and leaving the surface, and it's also related to how much it's changed, the density is changing with time.